Does this look about right? Oh, I did it again, didn't I? I thought that was a little squirrely looking because I saw Thursday there and okay, hold on. Sorry, I picked the wrong one. Monday, Wednesday. Hold on. Better? Okay. It's a long semester. Okay, so wanted to keep moving through 4. And we want to take a look at cell size. Remember, we talked a little bit last time about, we kind of got up to cell theory, kind of tied some of that stuff together. Now what we want to do is want to take a look at cell size itself and the limitation of cell size, right? So oftentimes a good question comes up. Students oftentimes will have a really good question to be like, well, how come the cell is small? How come you can't have a giant cell, right? Well, the reason is simple. The reason is because that if you're a single cell, you basically can transport things by diffusion. That's what you're working with. Now, the good thing about diffusion is it's easy, it's simple, it's fairly low cost. You don't have to pay anything for it. But as is the case, anything that's free, the value of that is somewhat suspect, right? There's a reason why it's in the trash can, usually speaking. And this is kind of like one of those things. So if you go like, you know, for saving expense, then you're obviously going to, you're going to be limited in what you can do, right? So that's kind of what we have here. So basically diffusion is very simple. You guys are essentially, you know diffusion. You already know it. You know it well, actually. You know, anytime you breathe, like on a cold winter's day and you see your breath, the reason why it disappears is because of diffusion, right? It basically diffuses out in the atmosphere. And so basically when you take a look at the idea of diffusion, and we kind of defined this already, right, with our osmosis diffusion lab, basically the idea of diffusion is this is the movement of solute molecules from an area of high concentration to an area of low concentration. And you don't have to do anything for it, right? So basically, if you take a look at diffusion, like for instance, if we put a drop of food coloring in a glass of water, what happens? It diffuses, right? So basically that one drop starts to spread out, right? And the water starts to turn kind of pink and the drop kind of turns a little less red. Well, where's the high concentration in the system? It's in the drop, right? The drop is where the high concentration of food coloring is. The water is low. And so the drop naturally moves by diffusion from high to low. So that's the reason why the drop spreads out into the water. And of course, it does that until what? When does it stop? Yeah, which looks like to you, like what would it look like to you? Like what would the glass look like? Yeah, it's kind of all mixed, probably a light pink color, right? But that's equilibrium. So you basically get diffusion, movement from high to low concentration until you reach equilibrium. And at that point, you're done. But this is basically how a cell gets things in and out of itself. So like, for instance, if you need to get nutrients into the cell, it's by diffusion. If you need to get trash and waste out of the cell, it's by diffusion. But here's the problem with diffusion. Diffusion's great, but it's also limited. Diffusion is limited by a lot of things, but primarily by size, by distance. Think about it. If I have a bottle of perfume up here and I open it, who's going to smell it first? Me, right? And then who? And you guys in the front, right? And then it's slowly, it's going to roll to you guys in the back, right? So what's happening is diffusion. You're going from the high concentration inside the perfume bottle to low concentration, which is on the other side of the classroom. So here's the thing though, if I had one of you guys like Mia, like if I'm sitting in the back of the room, if I had you come out the hallway, like go all the way into the hall, and then I opened up the perfume bottle, how long would it take for Mia to smell it? Would Mia smell it?
Yeah.
Like if she's all the way over there by the butterfly, would you even smell it? Would it get that far? Probably not, right? So why? Why wouldn't she be able to smell all the way at the end of the hall? Yeah, simple, right? She's just too far away. So diffusion, which is powerful in short distances, you guys smelled it right away, right? But if you're a long ways away, like down the end of the hallway, it doesn't work, it breaks down. So what does that mean then for you? So if you're committed to doing business by diffusion, which essentially cells are because it's cheap, then what you're also committing to is a limitation on your size. So if I insisted that everybody be able to smell a perfume, what does that mean? That means that nobody can get beyond the limits of that diffusion, right? That makes us have a small space. We're limited in size. So that's basically one of the drawbacks of diffusion. And as a matter of fact, a lot of times I kind of mention this because, you know, a lot of times, you know, we kind of look at biology a lot of times and we kind of think of it as sort of like driving through McDonald's, right? So it's like, I'll have this and I'll have that, and give me one of these and one of these over here. And it's like, well, that's not really the way it works, right? It's like, well, I want to be this size, I want to be big, I want to be small. It's not really the way it works in biology. Basically, the decisions that you make are associated only with your biological questions of life. That's it. The consequences of your decisions then basically are imposed upon you, and you live with what you live with, right? Here's a good example. If your energy strategy is to save as much energy and to kind of use a cost-effective pathway, the cheapest version of being able to get stuff in and out, because that's what you have to do, and you pick diffusion to do it, that's a good, smart, money-wise way to do things, right? That's a very frugal way to do things. It's not going to cost you much to do things by diffusion, but what's the consequence of that? The consequence of that is that you're not going to be very big. So a bacterial cell or an individual cell is small, not because they chose to be small, but because the choice that they made to answer the big biological question of life, one of the consequences of that choice was to be small. It's kind of like this. And Movina probably knows, I'm nothing if not repetitive. But anyway, you're like, sure. So if I, by trade, teach for a living, which means I don't make a lot of money, right? So, but that choice that I made didn't have anything to do with the downstream consequences. What is the downstream consequence? The fact that I can afford a 15-year-old Ford Escape, right? That's my car. Now, did I go out and choose, you know what, today I'm looking for a 15-year-old Ford Escape. That's what I'm looking for. And I'm not going to be happy unless I find that 15-year-old Ford Escape. No, that wasn't the decision process, right? The decision process was, this is what I want to do for a living. And this is probably about as much as I'm going to make. Now, does it have consequences? Yes. That means that what I can afford is a 15-year-old Ford Escape, not the Bentley. Right? If I wanted to be able to buy the Bentley, guess what? I probably should have made a different career choice, right? Something that involves a lot more money than teaching. So that's an example of the choices that you make early have consequences, and your reality oftentimes is the consequences of those choices. There's a life lesson in there as well, not just biology. But that's kind of the way the biology works, right? So a lot of times we kind of look at this as sort of like a post-consumer idea. And we're like, oh, well, I want to be big and multicellular, and that's how I want to put it all together. Well, that's not the way it all happened, right? You had to make initial choices, first of all. Like I have to solve the energy problem. How do I form enough energy to do the biology that I want? Well, you got a lot of choices. Some of those choices will take you down various consequential pathways. You become essentially the product of your choices. And that's the reason why things are small. That's the reason why you're limited in size. We'll talk more about that here in just a second. But before we do that, let's finish up the discussion. about diffusion. Since diffusion is kind of how you do business at the cellular level, the question is what affects diffusion and the rate of diffusion? Well, a couple of things actually affect it. Number one is the surface area. So basically your diffusional rate will increase with your increase in surface area. So the more surface area you have to diffuse across, then the higher your diffusion rate. Temperature will also increase your diffusion rate. So as you heat a system up, the molecules vibrate more, they diffuse faster. Okay, that's just basically how that works. Concentration gradient is a big one, not just concentration itself, but the gradient itself. So the greater your concentration gradient, the higher your diffusion rate. It makes a lot of sense, right? Because remember, you're always flowing from a high to a low, which means there's not equality there. There's a gradient. So the question is, how high is the high and how low is the low? Well, you have a couple of options here. So for instance, if your high concentration there is really high and your low is really low, then that is going to be a very steep incline, right? So this is your low concentration. So if you have that steep incline, that is a huge difference between your high and your low. This is going to be a very fast rate of diffusion. If I shallow it up a little bit, my high and my low are not quite as different from each other. This is going to be a slower rate of diffusion. And then of course, ultimately that proceeds until what? Until we reach flatline, equilibrium. This is basically no diffusion. As a matter of fact, by the way, you're using the same set of physics whenever you play like one of those little marble games. I don't know if you've ever picked one of those things up where you have like a little maze or something like that. And you're trying to like move the marble on this like little thing, like by tilting the little table, and you're kind of trying to move the marble around. You're using the exact same set of physics. What are you doing? In order to get the marble to move that way, what do? You raise it up here. What are you doing? You're increasing the gradient, if you will, on one side. And how fast do you want the marble to go? Well, it depends on how steep you make the pitch, right? If you wanted to move just very slowly, very gently, then you just kind of give it a little bit of a gentle incline. If you wanted to go blazing fast, then you basically give a steep incline. So the same set of physics is happening when you're playing one of those little marble games, as is what's happening here. We'll talk more about that in chapter 5. The other one, of course, is distance, and this is the big one, right? So basically, your diffusion rate will decrease with an increase in distance, and that's your big negative, right? That basically means it requires you to be small. Now, the question is like a single cell, that makes a lot of sense. But what about us, right? We're not a single cell, we're multiple cells. So do we have to deal with diffusion? The answer is yes. We have actually diffusion, and we've got another system beyond diffusion that kind of helps circulate things, right? So for instance, in order to get blood from our head through our heart back down to our feet, we obviously can't do that by diffusion, right? Because diffusion, this is just way too much distance there. It's never going to diffuse. And that's really a poor idea, isn't it? Because by the time you're waiting for that oxygen to diffuse into your lungs and diffuse out to the rest of your body, you're going to be dead, right? Because it's not fast enough, right? You need it now, not like when it's going to get here, right? So for instance, if I say, okay, this is a matter of life and death. If you guys can smell the perfume, you live. If you can't smell the perfume, you die. You got 10 seconds to smell it. I'm going to uncork the bottle. Is that going fast enough for you? Is it going to make it to you in 10 seconds? No. Will it make it to you eventually? Sure, but not in time for you to survive. So what do you want to do? Figure out a circulation system, right? That is, say, a transport system. Oh, guess what? We have diffusion, but you know what? Why don't I step a little closer to you guys? There. Now I brought it close to you guys. Now do you guys have a fighting chance of sort of getting this in 10 seconds? Yeah, but what do? We did a combination of diffusion, right, and circulation. That's what we do. We know that you're not going to be able to get oxygen to your tissues in time for you to survive. So what do? We create a circulatory system in order to circulate that oxygen quickly. And so we have a combination of things. We have a lot of tricks up our sleeves when it comes to human physiology. Okay, so let's take a look at the first one, right? The surface area, because this is an important idea, especially in the cell. So we already know that surface area increases diffusional rate, and diffusional rate will basically allow you to get the stuff you need, nutrients and things like that, oxygen in the case of our previous analogy. But remember, in order to get more surface area, you have to get more cell. And remember, since cells are three-dimensional, you don't just get two-dimensional cell, you get three-dimensional cell, which means volume. Okay. Now you can take a look at surface area as a good thing, right? The more surface area you have, the more diffusion you get. That's a good thing. This is kind of like your working area. This is your working surface. It allows you to do more work. So it's a benefit. However, the volume is the size and its costs. So this is a cost. So really, when you look at surface area to volume ratios, it's a benefit cost analysis, just like you do in economics, right? In economics, whenever you're looking for a good deal, what are you looking for? Maximum cost for minimum benefit? Yeah, the other way around, right? You're like, wait a minute, are you tricking us? Yeah, a little bit, right? Yeah, no, you're looking for maximum benefit for minimal cost. Preferably, you want the whole world for free, right? That's what you want. And your cell's the same way. But here's the problem. If you have working space, like your surface area, and you say, well, I need more working space. Well, if you need more working space, you can go out and purchase more working space, can't you? But guess what? You're going to have to pay more for it, right? The question is the cost, is the increase in cost a deal, right? Versus the benefit that you get. So that's what we want to get. So what we want to do is we want to get maximum benefit. We want to maximize your benefit for minimizing your cost. Now, here's the thing. A lot of times, if you use the Texas mentality, a lot of times the initial way of saying, oh, this is how you maximize benefit, just increase your cost, make it bigger. If you need more surface area, that means you need more cells, so just make it bigger. So increase the size. That'll increase your volume, but it'll also increase your surface area. Well, that would be a good idea if it were a one-to-one increase, like for every unit of surface area, you increased 1 unit of cost, but that's not the way it works. The way it works is that actually volume increases by a lot more, making this idea not a good idea. Let's take a look at it. We're going to take a look at two cells, little guy here and big dude. And we're just going to take a look at some of its parameters. And these are just generic units. We don't really care about what the units are. We're just doing a relative comparison just to drive home the point. So the first cell, we're going to have a radius of 1 unit. Now remember, radius is basically going to be a straight line, and it's not three-dimensional. So we have to factor in 3 dimensions because you have a radius going in all 3 dimensions. So you have to factor that in here in just a second. So you have 1 unit radius. Now, if we basically increase our cell 10-fold, 10 times, then the idea is we should get more surface area, right? Well, let's go ahead and do that. So we're going to increase our cell 10 times, and we're going to use the Texas mentality. We're going to prove to ourselves that this is not a deal if we just do this. Well, what do we get in surface area? Well, surface area, which is 4 pi r squared, in this particular case, is going to be 12.57 units. And don't worry about the math. I'm not going to have you calculate the surface area of a sphere. It's never going to happen, right? Maybe in biophysics, perhaps, but not in this one. Well, if we increase this 10-fold, then it goes up to 1257. Not so bad, right? Starting to look good. You just increased your surface area, your working area, your productivity, if you will, by what? 100-fold, didn't you? 2 movements of the decimal point, right? 10 and then 100. So that's not bad, right? For a 10-fold increase in size, you get a 100-fold increase in surface area. Does that sound like a good deal so far? Well, let's keep following this through, right? Because it's not just about surface area. Remember, your total cost or the radius is not it's not three-dimensional. This is only a single dimension. So we have to factor in what this cost would be for all 3 dimensions because cells are three-dimensional. So we have to take a look at the volume, not just the radius. So the volume is going to be 4/3 pi r cubed. And it's going to give us in the first little guy a 4.189 unit volume when we increase the cell size in all 3 dimensions and factor that in. Then it becomes 4189. Notice what that is. What is that? That is a 1,000-fold increase in what? Your cost, right? So what you just did was you got a 100-fold increase in benefit for a 1,000-fold increase in cost. Is that a good deal? No, that's like buy 5 for the price of 10. You gonna go for that one? No, right? Because you're paying more than you're getting benefit for. It'd be better to buy them singly, right? One at a time. So if you take the ratio surface area to volume, you notice that you have a surface area to volume number of 3, but you notice it goes down. The difference is a 10-fold difference, but it's going in the negative direction. So when you factor in your costs, did you get extra surface area? Sure you did, but you paid more for it. Bad deal, right? So this is bad energetic economics. Your cell doesn't want to do this, but here's the problem. It still has to increase surface area, right? To get maximum productivity. So how does it do it? Simple. It does some tricks. So here's a cell, just a basic rectangular cell with a certain volume to it. So how do you increase your working area? Well, let's take a look at this. Let's say that's right there is the working surface. That's it. Not all the rest of the stuff. This is attached to other cells and things like that, right? So how do I increase my surface area at that particular place without increasing my volume, right? How do I increase my benefit without increasing my cost? It's a simple trick. What your cell does is it starts to mess around with surface area. So it'll take the cell and it'll do something crazy like this. Roughly the same volume, but more surface area now, right? Because instead of just this one surface to work with, now it's got all this surface in between these little nooks and crannies. So now what you've done is you've increased your surface area for the same amount of volume. All you did was modify the way your cell looks. This is a common theme, actually, you see throughout biology, where you see lots of structures that are designed to increase your surface area and keep your volume the same. So that's and the reason why the biggest reason why I make that point is because we see it enough to where it bears an explanation of why we see that the way we do. Okay, let's take a look at some of our microscopes. So you guys have already used microscopes, right? Because you did labs 5 and 6. So basically, when you take a look at a microscope, for the most part, obviously, a lot of things that we're looking at in microscopy are not visible to naked eye. So there are a lot of them are like going to be in the range of less than 50 microns in diameter. So that's pretty tiny. For your naked eye, it has to be around 100 in order for you to be able to see something with the naked eye. So most microscopic things are well below the threshold for visible, for seeing things visibly. So what exactly are we doing in microscopy? What we're doing in microscopy is we're increasing the resolution. So if you recall on the microscope, there's 2 numbers, the X number, and then there's another number next to it. That was the resolution number. And so the resolution, simply put, is your ability to be able to distinguish 2 points. That's all it is, as separate points. So here's a good example, and I always like to kind of do this one. And I'm going to use Mia again, since she's in the back. This is one of those ones where I use people back. But when you take 2 different points, right? So for instance, if I just put a point here and a point here, can you tell that those are 2 points? Pretty simple, right? Now, what if I get closer together? Can you tell that those are 2 points? Sure, not too bad. How about if I get closer together? Can you tell that those are 2 points? So it's kind of starting to look like a blob or a dash, right? So what I've done is I've hit the limit of resolution. So can you guys in the front see it's 2 points? Yes, but Mia's starting to see more of like a run together, right? So that's the limit of resolution in that case is somewhere right in the middle of the room. And so the idea with microscopy is it basically magnifies this image so that you can see that there's clearly 2 dots right there, right? So for instance, I would represent like the lens, I can see it's up close and I can see clearly that it's two dots. And that's what resolution is. And that's basically what microscopy is doing. So there's two different types of microscopy. There's light microscopy, which is the one that we've been using, right? So what this does is it uses light as the resolving particle. And this limits us, right? Because light is actually always a resolving particle, by the way. That's what we already saw that, right? Because in the microscope, you've got that little condenser contraption underneath the stage. That's to help focus some of that scattered light. If light is scattered, it creates an image that's blurry for us, right? The more focused a light is, the sharper it is. And so what the light does is when it's scattered, is it has to be able to reflect off of an object. So what we actually see is not an actual physical object. We're seeing the light that's reflected off of that object, right? So technically speaking, I'm not looking at you guys. I'm looking at the light that you're reflecting back to my eyes. Okay. And those are photons. The same thing's also true here. So as long as my light, my photon of light, which is my resolving particle, is smaller than my sample, I'm good, right? So for instance, if I have this case here, where here's my sample, and here's my photon of light. If my photon of light hits the sample, it'll basically reflect off, and then I can see it, right? However, what happens if my sample is smaller than a photon of light? What happens if I've got a little tiny sample, but my photon of light is like this? Am I going to be able to see that? That's not going to happen. Why? Because the photon will just basically envelop your sample and it doesn't have anything to bounce off of. Okay. And so that's the limitation of the photon of light. That limitation gets us down to the ability to see things that are about 200 nanometers apart. Not too bad, right? You're going from 100 visible naked eye to about 200, that's 100 micrometers, by the way, to now 200 nanometers. That's not too shabby, okay? However, there are still some things that we want to see that are fairly tiny. And none of that, but even though we can see them with the light microscope, here's a good example, organelles. You guys saw organelles, right? You saw some of these little critters floating around and you saw them and they kind of had like little bubble looking structures inside them. Those are organelles. So you can see organelles, right? But the thing is with light microscopy, the limitations are such that you can't see them well. So what if you wanted to get a really good up close look at it? Well, then you want to switch to a different resolving particle, okay? And that gets us down to the electron microscope. So now the resolving particle is an electron. Resolving particle, thinking like 16 different things at once, and they're all kind of coming out half baked, right? So the resolving particle is what? An electron at this point. How tiny is an electron? Is anything tinier? Yeah, even a proton is bigger than an electron, right? So this is now your resolving particle. And so with electron microscopy, what you're doing now is beaming light at your sample, you're beaming electrons at your sample. What this does is it creates a lot of crystal clear structure, and you can get resolution down to 0.2 nanometers, much, much better, right? And so now we can see those organelles, but we can see them up close and personal. So we can start to see things like mitochondria and chloroplasts and what they actually look like. A lot of structure. This has been an enormous leap in the 20th century for cell biology, where we've actually been able to, instead of indirectly measure organelles, we've actually been able to structurally, visually look at them and actually diagnose their structure and see how they look. That's been enormous. And a lot of our cell biology now has been benefited from the electron microscope. However, the question always comes up, And I always like to sort of get to that one initially. A lot of times students will be like, well, wait a minute. So if an electron is vanishingly small, as you said in chapter 2, and it's smaller than a proton, does that mean we can see a proton with electron microscopy? Theoretically, you would think so, right? Because the electron's smaller, it should bounce off of the proton, and you should technically be able to see a proton, right? But you can't. And there's a good reason for that, but it's not necessarily satisfying. And the reason for that is simple. It's quantum mechanics. Because one of the things that you know in physics, when you kind of get into sort of particle physics and stuff like that, is that the universe is largely governed by the laws of relativity, which are very predictable, very calculable. That makes a lot of sense, right? So when we're out here in the macro world and in the universe, it's relativity that reigns. But then as we start to get smaller and smaller and smaller, like down to the macromolecule level, we can see macromolecules, we can see proteins with electron microscopy. But as we start to get smaller down to the atomic level, all of a sudden, it's like the universe is governed by a different set of laws. It's like they change the rules of the game on you, like right in the middle. And phenomena then switches to the quantum mechanics level, which is very unpredictable, very paradoxical in nature. And it's just a crazy world in there. And that's part of the fun. That's why the particle physicists love particle physics, is because of the craziness of quantum mechanics. But the idea of quantum mechanics, that sort of paradoxical shift of quantum mechanics is what sort of scuttles the capacity of being able to do the straightforward type of detection with electrons, is because they just don't work the same way at that level. For reasons that is beyond my degree pattern. I have to get into particle physics to explain that one a little bit more. But I have no intention or desire to do so. But that's kind of what it is. It just kind of, the laws of the universe sort of break down, and then they kind of shift to a different set of rules at that point, and it kind of changes the rules of the game. And that's, by the way, something that is not just, I mean, that's a rub between quantum mechanics and relativity that has scuttled and defeated many great minds, including Einstein himself. And it still is a head scratcher for particle physicists, because it doesn't add up, right? It doesn't make sense that, okay, if the entire universe is rested on quantum mechanics, then the universe should look different than the way it is. So why does it look like one reality governed by relativity up here, but then down here, it's a completely different ballgame? We totally wouldn't predict it. It doesn't seem like the two add up, right? So how can something at a small level of reality be existing in opposition to something at a larger level? So there's kind of a disconnect there. But that's kind of what particle physicists are paid to think about, not me. Okay, so let's take a look. There's two different types of electron microscopy. There's transmission, which essentially is beaming electrons through the material, kind of like a cross-section of material, and then the scanning, which basically will beam it across the surface. And then you'll kind of detect it. So one is you basically have a cross-section where you beam the electrons through, and the other one is you just kind of glance it off the surface. The surface one, the scanning, will give you kind of a three-dimensional topographical view of the structure itself, which is kind of cool. Okay. So this is just kind of like a relative sense of size and scope. So you notice visible eye can get you down to fairly small stuff. I mean, you gotta have pretty good eyes to see paramecium, but I guess you could. And then of course down here you have light microscope, but you notice it overlaps with electron microscope. Because so these things, like for instance, can you see a prokaryote light microscope? Yes. Can you see it better with electron microscope? The answer is yes, right? Because your resolving particle is much better than electron microscopy. So that's kind of where, so notice you kind of get down here to the protein, the amino acid level, hydrogen atom, notice you're kind of beyond. That's where quantum mechanics sort of kicks in. It's sort of, you just change the rules of the universe on yourself right there. But this is what the different types of microscopy look like. So the light driven ones are basically these four. So the first of all, bright field, that's basically what you guys use. That's a kind of a fancy word for the light microscopy that you guys just did in lab. You're just looking at critters and you can see that's just basically allowing light to sort of pass through your specimen and sort of do that whole little bouncing back and forth off things, being deflected by things and sort of creating that shadow play. That's all it does. Another version of light microscopy is dark field. So dark field is kind of a flip side. So what it does is it kind of has a special condenser, which is that little contraption underneath that sort of plays with the light a little differently. So it has actually kind of a dark background and it lets the light pass through a very small ring. No, Megan, I just showed this just to kind of show you the different possibilities. Most of our microscopy work is associated with just our basic standard light microscopy, but this kind of gives you an idea of what the possibilities are, right? So this basically will shine light through the organism, so it looks like a photo negative. It's actually quite useful. Phase contrast does a sort of a similar thing. So light basically will kind of have different like types of waves where it'll kind of like, you know, kind of create phases and to sort of kind of manipulate what light as a wave particle. So these are wave light, just taking advantage of the physics of light as a wave, both of these guys. So you have like to call the phase contrast, and then you have what's called interference. So differential interference or Nemarsky. This is a situation where you take polarized light and you beam it through here, and it kind of creates this sort of translucent, sort of bas relief looking structure. This is one of my favorites, right? So you can see it's the same thing, just different manipulations of how you're kind of playing around with light. It's optics. It's all about optics is what it's about. And so, but they're all just variations of light microscopy. Now, these two down here are cool because these are fluorescents, right? So remember we talked about fluorescence in chapter 2. This is where you have a high energy source that it gets that absorbs the energy gets absorbed by the electrons, which then jump up to a high energy state. And then when they fall back down, they emit a photon of light. That's fluorescence. Well, in this particular case, what we've been able to do is we've been able to basically take a protein of interest, something that we want to know or learn about, and we've been able to figure out how to actually tag it with a fluorescent molecule so that wherever this protein is made, it's going to be carrying our fluorescent tag. So it literally, it's just like turning the lights on. Normally that protein is invisible to us. We have no way to see it, but now once we have that fluorescent tag on it, we have a way to see it. What do? We shine basically UV radiation, and then that fluorescent tag will absorb the UV radiation. The electrons will get excited. They'll jump up to a higher energy state. And then when they fall back down, they'll emit a photon of light. And we can see that in this particular image. So here you can see you've got this yellow is some sort of a protein that we've tagged, and it's emitting this yellow fluorescence. So we can see that wherever that protein is where the yellow is. And we've learned a lot about the position of the protein, because a lot of times we have questions of like, okay, protein X, where are you? Where do you work for a living? When are you there, right? Because we've got lots of developmental stages. It's like, are you just only on during a certain point of development and then you never see you again? Or are you on all the time, right? What tissues are you on in? Are you only on in the liver and never seen in the brain? So these are what's referred to as expression patterns. Let's give us expression studies. So the way that a gene expresses itself through its protein and the behavior of the protein, we'd be able to visually see and record through fluorescence. Now, another version of this fluorescence is using lasers, right? Because a laser is the ultimate focused light. Remember I said that more focused light is, the more sharper and clear the image. This is absolutely true in confocal microscopy, where instead of just using like a UV lamp to excite your fluorescent molecule, it uses actually a laser. And this laser usually you can program to be at a very specific wavelength. So instead of just having just a general UV lamp, it's actually going to be like, I can actually calibrate this to be very specific wavelengths and just point that right at my fluorophore, which is what they call the fluorescent molecule, and then it'll fluoresce. But because it's very targeted and very focused, the laser light is, it's going to give you a very sharp image. And that's exactly what you see here. Notice how crystal clear this is. So this is the neuron, and this is also the neuron. This is the same tissue. Notice how much sharper and clearer this image is. That's what confocal does for you. So confocal microscopes are really beautiful. I worked on them in grad school. They produce some really beautiful images. But those confocal microscopes are immensely expensive, as you would well expect with lasers and things like that. And it usually a lab doesn't have them. It's usually several labs that go in and kind of share the costs of a confocal, because once you get a confocal, not only is the price for purchase very high, but then you have to hire somebody who kind of runs it and who kind of takes care of it, make sure all the lamps are up and running and things of that nature. So the maintenance costs of a confocal microscope can be quite high as well. And that's the reason why oftentimes labs will go in with each other, right? They're like, listen, I can't afford a confocal, but I'll go in with 3 or 4 other labs who want to get a confocal, right? So Anschutz has one of these. Boulder certainly has one of these. I don't know if they have one in this building. If they do, it's probably in the basement somewhere. Probably like, nobody can touch it kind of a thing. But these are really beautiful. We've got a lot of information, tons of information from confocal and just fluorescence microscopy itself. Now, what about the electron microscopes? Well, these are the two. So here's your transmission electron microscope and micrograph, and this is your scanning electron micrograph over here. So here you can see you basically got this cross section of a cell, so you can see the individual organelles, and this one is sort of like this nice cute little picture of a furry little guy, right? This is probably a bacterium. And so this is basically kind of your topographical view. This is what it would actually look like if you were to sort of miniaturize yourself and sort of fly into it and sort of take a look at it and see it. That's what the cell would look like. So that's your scanning electron micrograph. So let's take a look at some of the basics of cells, right? Some of the things that cells all need. First of all, they all need genetic material. DNA equals life. Why? Because DNA is all of your information necessary to make you from scratch, right? So if you don't have the information or the blueprint to make you from scratch, then guess what? You don't exist, right? So that's why DNA equals life. And in this particular case, it's usually got to be centrally located, right? Some sort of a central location for your genetic material. So that's a common thing. Cytoplasm. All cells need to have cytoplasm. Now, there's a couple of terms here that I want to mention. The term cytosol, which is basically just the fluid inside the cell, and the cytoplasm, which is the fluid plus all the organelles. So the reason why I want to point that out is because the term cytosol is like an older term. As a matter of fact, I oftentimes can tell what generation of scientists you learned your biology from by just whether or not you use the term cytosol or not. Because only the older generation uses that term. Because the older generation used to see the cell as just being this vast expanse of fluid, cytosol, within which are these little islands of organelles floating around occasionally. Okay. So for them, the term cytosol made sense. But in reality, what we noticed was that's not the case, that the cell is so choked with organelles that there's very little visible fluid in between them. And so really in practice, you always refer to the term cytoplasm. As a matter of fact, even the, Catherine Howell, who's one of the big cell biologists at Anschutz, most of the time she uses the term cytoplasm to refer to it. The only time, however, she's ever used the term cytosol is when she's very specifically distinguishing the difference between the fluid, like if something's going into the fluid of the cytoplasm versus somewhere else. That's the only time I ever heard her use the term cytosol. But like if she's just talking about, oh yeah, this thing comes into the cell and then it enters into the cytoplasm, that's the term. They don't ever say cytosol, okay, unless they're distinguishing the fluid from the non-fluid portion of it. And even then, the newer generation doesn't use the term cytosol. They'll use the term like the fluid of the cytoplasm, right? That's what they'll say. So everybody has to have a cytoplasm. Everybody has to have DNA, and it's going to be centrally located. Everybody has to have a plasma membrane, which makes a lot of sense, right? Because the plasma membrane is what actually creates the boundary for the cytoplasm. I want to add a fourth one on here, however. Ribosomes. Basically, these are protein complexes that make protein. Another one of those little circular sorts of things, right? But that's what these guys are. So these are protein complexes whose job it is to make proteins. Okay, let's take a look at the simplest. And this is going to be a pattern we see throughout the semester. We start off with a mechanism, and we're going to be talking about prokaryotes. What is it like in a prokaryote? That's the simplest system, bacteria. That's where we started. In the 50s, 40s, 50s, and 60s, we started with the simple stuff, right? Bacteria, easy to grow, easy to maintain. We get buckets of it, fairly simple system. So we're always going to see this pattern. Start off with understanding the mechanism of prokaryotes, and then immediately we transfer that knowledge to eukaryotes. And we ask, okay, do eukaryotes do it the same way? And if they do, then how do they do it, right? So basically, we kind of expand the idea. We say, what are the new bells and whistles and things like that the eukaryotes do, right? So let's take a look at prokaryotes. So first of all, in prokaryotic cells, there's a couple of things that stick out. First of all, they're not only the simplest, but they basically have no membrane-bound nucleus. As a matter of fact, they have a central location for their DNA. That's true, but it's not a nucleus. It's not a membrane-bound compartment. It's what we refer to as the nucleoid region, which is kind of like, sort of like, instead of having a closet, which would be like a structural encasement for your clothes, what you have is the southeast corner of the floor of your room. And that is the clean pile, right? Right. So you throw your clothes on the floor in the southeast corner. That's the clean corner. And the dirty clothes go in the southwest corner, right? That's the dirty corner. Now, the question is there a centrally located region for your clean clothes? Yeah, the southeast corner. But is it structured within an actual little mini room, like a nucleus? The answer is no. But you do have a central location for it, right? So the nucleoid is kind of like throwing your clean clothes in one corner of the room, but that's where all your clean clothes go. Okay. They have a cell wall, so that's an important piece there. They contain ribosomes. Everybody has to, right? If you're going to be making proteins, which are the ones doing all the work in the cell, then you've got to be able to have the manufacturing to be able to make them, and that's what ribosomes are. And they have no membrane-bound organelles. Do they have organelles? Yes. Ribosome is technically considered an organelle, but they don't have any membrane-bound organelles. Okay, so so that's basically the prokaryotes. So when we take a look at prokaryotes, they compose two domains. They never used to, right? It used to be they only had, two domains, prokaryotes and eukaryotes. But what we noticed was of the prokaryotes, we actually have two very distinguished flavors, if you will, of prokaryotes. First of all, archaea is one of the bacteria, is the second. So in domain bacteria, you see bacteria-like. So that's where we have things like E. coli, salmonella, staph, and stuff like that. And then in archaea, typically these guys are extremophiles. What does that mean? They live in harsh environments, like deep sea thermal vents, for instance, right, where you have an extreme pressure, extreme temperature, and all sorts of problems going on down there, right? So these guys tend to be extremophiles, but they tend to behave very differently. So let's take a look at the basic structure of the prokaryotic first, and we're going to take a look from the inside out. So here you can see your nucleoid region. So this is your genome. It's all wadded up, tossed there in the middle. So this is your nucleoid region. As you start to move out, you can see these like little itty bitty dots. Those guys are the ribosomes. Those are just floating around in there in the cytoplasm. And then as you continue to move out, you're going to run into this first little layer on the outer wall complex. This is going to be your plasma membrane, your lipid bilayer. So there's some lipids there that are a little bit different than what we see in a eukaryote. And then as you keep going out, you're going to run into another layer. This is going to be your cell wall. And then another layer outside of that, which is your capsule, which is typically kind of a gelatinous sort of a layer. And these guys are going to be primarily for protection. And then attached to the capsule, you're going to see these long hair-like structures, the pilus. And the pili basically will give you the capacity to either bind to something or to connect to another bacterium, right? So for instance, bacteria are able to swap DNA between each other. It's a process called conjugation. It's not really like mating per se, but they can do this through what's called a conjugation pilus. So they just basically kind of connect this little pilus to each other, creates like a little tube between each other, and they can kind of swap stuff back and forth through that little tube by conjugation. So what are they swapping? What they don't show on this one that's going to be important actually for later on in the chapter is that bacteria also have, in addition to this nucleoid main genome. So this is their main genome. Right, so when they go through replication, that's what they're dealing with. But then there's another little piece of DNA, a little circular piece of DNA called a plasmid. And this can be swapped back and forth between bacteria. So when you're doing a conjugation, that's more than likely what you're going to be doing. So on this little ring of DNA, you can have things like antibiotic resistance genes on there, mating strains. So bacteria don't have gender. They have like F prime and F. They have different strains that they can conjugate with, like an F prime would conjugate with an F, not another F prime. But you can swap these little cassettes of DNA back and forth between the bacteria. And it's one of the ways that the bacterial population can kind of make use of like beneficial DNA. Like, hey, I've got a really useful bacterial, like a resistance to antibiotics. Let me go ahead and conjugate that to you and kind of swap it around. And so this is an important piece, another secondary source of DNA that's kind of unique that bacteria have. So the other thing that we also have is the flagellum, right, which is a large whip-like structure that's largely for locomotion. So let's take, first of all, a look at the cell walls. So a bacterial cell wall is strong. It's largely there to protect the cell, but it's going to be made out of peptidoglycan, which is kind of a protein carbohydrate fusion protein. So it's kind of a fusion of both protein and carbohydrates. So peptido for the peptide, that's the protein part. Glycan for glycogen, right? That would be the carbohydrate component of it, which is a very different construction than, say, for instance, the plant cell walls. What is a plant cell wall made out of? Ooh, good thing the exam's not this Thursday, it's next Thursday. It's made out of what? The eyes are squinting. Hang on to that one.
Oh.
Not yet. It's the other one. Yeah, good. Which one? Yeah, cellulose, right? So plant cell walls are made out of cellulose. Now, what's fungal cell walls made out of? Now, yep, it's made out of chitin, right? So those are the structural carbohydrates, those structural polysaccharides we talked about in the last chapter. You might want to go back and revisit that one, right? So different construction than peptidoglycan, but it's basically the same idea. It's for protection. It's for shape. It'll maintain the shape of a cell, and it also keeps you from blowing up, right? So basically keeps from lysis. So first of all, protection, right? bacteria, the bacterial existence is not for the timid. Everybody wants to kill you, right? I mean, literally everybody in your environment wants to kill you. So that's the reason why you have like armor, right? You have multiple layers of armor. That's where you have a cell wall to protect you. Then you have a capsule to protect you. And so you've got lots of layers of protection because everything wants to kill you. Not only that, but you're swimming around in water, right? Remember when we said the mantra of osmosis was? Salt sucks, right? So if you have like a salty prokaryotic cell, what's water going to naturally want to do to that cell? Yeah, it's going to want to come into the cell. What's going to happen? It's going to fill it up, right? And it's going to burst like a water balloon, isn't it? Unless, of course, you have a cell wall, which basically means let water come in all at once. It's not going to hurt me because my cell walls will keep me from bursting. Okay, that's the game. That's the water loss protection. Cell walls are also what we use to target our antibiotics with. So our antibiotics are actually targeted at cell walls. Matter of fact, you'll learn this in micro if you take micro. We actually categorize bacteria into gram-negative and gram-positive by the construction of their cell walls. There's two fundamental patterns of cell wall construction. And antibiotics often will go after those patterns because those patterns are unique to bacteria and they don't look anything like what our cells look like. So it's like they're very foreign. So antibiotics will go after those and they can preferentially attack the bacterium with those cell walls. And that's kind of what they go after. And so some of those cell wall components are common to both strains of bacteria. That would be like a broad spectrum. And some of them are more specific to like gram-negative or gram-positive. And this is also the reason why we have these different types of antibiotics, which are kind of like either broad spectrum antibiotics, which is going after a general wall structure of bacteria, or things that are like a little more, or that you kind of get these families of antibiotics, right? So there's a particular group of cell wall structures that a particular antibiotics is designed to recognize. And that'll be like, you know, this is going to be like the tetracycline family, right? And it'll go after this one particular type. And then another antibiotic will go after a different structure of the cell wall. And it'll kind of create different families of antibiotics. And that's basically what we've got. Archaea is a little bit different, right? Because although it's prokaryotic in the sense that it doesn't have any membrane-bound organelles, it doesn't have a nucleus, it doesn't have any of that stuff. So that makes it prokaryotic. But it's very unlike bacteria, right? So this is basically, it's prokaryotic. But unlike bacteria. How? In its cell wall. So it doesn't have a peptidoglycan cell wall. It's got a different type of polysaccharide protein construction. That's not the exact same molecule as a peptidoglycan wall. Not only that, but the lipids that it uses in its membranes are different than what bacteria uses. But here's the real kicker. Even though structurally archaea look very prokaryotic and resemble bacteria, so that's the reason why we often have to say like, oh, well, this is a bacterium. What it does is very non-bacterial. As a matter of fact, when we take a look at the mechanisms of the way prokaryotes do DNA replication, protein synthesis, and things like that, and the way eukaryotes do it, archaea actually look more like eukaryotes when they do their fundamental mechanisms. So they do replication like a eukaryote does, not like a prokaryote. They do protein synthesis like a eukaryote does, not a bacteria. So archaea kind of sit right here in the middle. They're kind of like, if you were to look at prokaryotes and eukaryotes and kind of do like a little Venn diagram and sort of like overlap them, then in that overlap, so if this is bacteria, this is eukarya, then in that overlap would be archaea. Some of its features look very prokaryotic and very bacterial-like. Some of its features look very eukaryotic-like. But it's kind of its own thing. Okay, let's take a look at the flagella and the structure of the flagella, because we're going to circle back around. We're going to take, this is the prokaryotic flagellum, and we're going to circle back around. We're going to take a look at the eukaryotic flagellum and kind of do a little bit of a comparison. So first of all, when you take a look at the flagella, in prokaryotes. You can have one or two or three, so you can have them on either end of you. So you can have like one like this, or you can have one like that, or you can have a whole bunch of them. And so there's lots of different types of bacteria with different types and numbers of flagellum. And we have an entire classification system in micro that you'll learn about in micro if you take like micro. So you can have lots of them, but they're all doing the same thing. They're all for locomotion. This basically allows the bacteria to move. Okay, how does it do so? Like a boat propeller. So it's a rotary motion. That's what it is. So if you take a look at a boat propeller, the way a boat propeller moves is it rotates, right? And then in rotating, what it does is it pushes against the water, which pushes the boat in the other direction. And the flagellum is doing the same thing. So it gets this kind of rotary motor action, but it's driven by what's called a proton gradient. Now, what's a proton gradient? Basically, remember, a proton is equal to a hydrogen ion. Remember we talked about that? Why? Because if you take a look at hydrogen, it has how many protons in it? One. How many neutrons does it have? You can tell by the mass number, right? How many neutrons does it have? Or, yeah, right? Why? Because the mass is also one, which is exactly the size of one large atomic particle, nuclear particle, which is either a proton or a neutron. In this case, it already has one proton, so there is no neutron. How many electrons does hydrogen normally have? One. Now, what happens if we take that electron away? What do we have left? If a hydrogen atom is one proton and one electron, if we take that electron away, what do we have left? It's a proton. Basically, the hydrogen ion is a proton. This is the reason why you hear this terminology fluidly. Like, for instance, if we're talking about pH or acids, we usually use hydrogen ion, right? If we talk about physiology and mechanics, we oftentimes talk about protons, proton gradients. It's the same thing, because a proton is a hydrogen ion and a hydrogen ion is a proton. So what does this mean? This basically means we use the proton gradient kind of like a hydroelectric dam. What does that mean? So that basically means if you look at a hydroelectric dam, we'll talk more about this. Basically, you have a big volume of water behind the dam and not so much in front, yes? What you have is a gradient, don't you? Behind the dam is high energy. Below the dam is low energy. So what you can do, and what we do with a hydroelectric dam, is we convert that energy to electricity. Why? To light Las Vegas, right? And how do we do that? We allow the water to flow through the turbines, which are inside, in this case, Hoover Dam. As they spin the turbines, then out comes electricity. So how did we get electricity? By utilizing the gradient, the energy gradient in the dam. So a proton gradient is exactly the same set of physics. The only difference is you've got an energy gradient, you're using it the same way. The only difference is instead of water, it's a proton. So this is how we use it. Here's our flagellum. So if you take a look at our wall construction, you can see we start off with our plasma membrane. In our plasma membrane, we're going to have two ring-like rotor proteins that are embedded in that membrane. And they're rotary, so they have the ability to sort of rotate around. And then in your wall complex, which has kind of like an inner and an outer layer. So you have the inner peptidoglycan layer, and you kind of have an outer layer as well. Inside these layers is going to be another set of rotary proteins that are able to sort of spin around. And then through that is a shaft-like protein that bends into what is the flagellum. So you can see here, the flagellum is this long sort of filamentous structure, kind of hooks. And so basically kind of creates this like little hook on the outside. and it's tethered to, like a shaft, to rotary systems of proteins. So these guys will basically rotate. Now, what happens? How do you energize this? How do you make it rotate? Well, what happens is you have a high proton gradient out here, a low proton here. So what happens is normally it wants to flow from high to low, right? So just like with the dam, we allow that water to flow from high to low, but we let it flow through our turbines. And this is kind of like the turbine here. So basically going to flow through that turbine. And as it does so, it's going to release energy. And the energy release is going to be enough to rotate that little shaft. And as it rotates, it's going to spin the hook like this. Now, if you allow a lot of energy to do that, then eventually what's going to happen is that's going to keep rotating around, and you're going to get this little propeller rotating structure where you have this guy right here. So it's basically rotating just like a propeller, and that's enough to sort of push that bacteria through the water and through the fluid. So this little guy then is going in that direction. Just like a boat propeller, you're pushing the water in that direction, which forces the cell to move in the opposite direction. Okay, so now let's take a look at eukaryotic cells. What's the deal with them? Right. Well, first of all, they've got a membrane-bound nucleus. That basically means they've got a closet for their clothes. That's like their cellular closet for their DNA. They are more complex, but compartmentalization is the key here. How do they do that? By basically creating these membrane-bound organelles, and not only that, but each of these organelles can answer a big biological question of life. Not all of them, but just one of them. So what you get with division is with compartmentalization is division of labor. That increases your productivity. Think about it. You guys, here's a perfect example of compartmentalization and the productivity benefits of compartmentalization. This room is just a big open space, yes? If we didn't have any desks in here and you guys were here, would you guys be as productive? You would have nowhere to put your stuff. You wouldn't have anything to write on. You would just be kind of milling around. There wouldn't be any sense of like, okay, this is kind of my working area. It would just be all together. You would have a certain amount of productivity, right? But would you be maximally productive? So all I did then by putting desks in the room was to compartmentalize the space. Now everybody has kind of like their own little place to work, don't they? Now all of a sudden you have like a little surface to write on. Now you can take notes. Some of you like to just pretend like they were like over here, like maybe there's like wall plugs in the outlet. So you have a place to plug in your computers to recharge or things of that nature. So you can basically set up even more productivity. Why? Because you have a place to do it. Now, Mobina's typing on her laptop. If she didn't have that desk, would she be able to do that? But you would have to sit down somewhere. There's nowhere to sit. So you'd be on the floor. It would be very, very inefficient, right? Is that the way you want to write your 600-page novel? No, right? So all I did by compartmentalizing the space is I divided up labor. I said there's areas of this room that are designed for one purpose, like walking, like for instance, the aisles in between the desks and the front of the room. And then there are other areas in this desk that are designed for work, for writing, your surface, the tabletop. By the way, there's also parts of this that are designed for storage, right? Take a look underneath your desk. There's a little basket there so that you can put stuff that you're not currently using, right? So now what have I done? Within the compartmentalization concept, I've created from one space that's ill-defined to 3 major spaces where there is a division of labor. All 3 of them together answers all of our needs as students, right? But any one of them doesn't answer all of our needs. That makes sense? So, and that's kind of what compartmentalization does. It divides up labor and it organizes your tasks so that you can get more accomplished. There's a couple of things that really stand out in eukaryotes that are like the innovations, right? So for instance, if anybody would ask you, it's like, well, what is the big innovation of eukaryotes? Like, why are they so much better? That's a very eukaryotic thing to say, right? Than prokaryotes. What stands out? Well, the 2 things that stand out are the endomembrane system, which we'll talk about here in this chapter, and the other one is the cytoskeleton, right? The cytoskeleton is simply just a support structure. It's a skeleton within the cell itself. It's a framework within the cell itself. Prokaryotes don't have that. Okay, eukaryotes do. And these are really 2 big innovations associated with eukaryotes. So let's take a look then at some of the features of eukaryotes. First of all, plasma membrane, is that unique? This is true for all cells, yes? Cytoplasm, is that unique? That's also all cells. Organelles, is that one unique? That's eukaryotes. Cytoskeleton, is that one unique? Yeah, we just said that is, right? And then of course, nucleus, is that unique? Yeah, eukaryotes, that's a eukaryotic thing, right? So you can see the bottom 3 of this list are innovations of the eukaryotes. They divide up labor through compartmentalization of the organelles. They can get more done in a smaller space. They added the cytoskeleton to give them structure and framework, which they use to their benefit. And then one of those organelles is a place to put your DNA, right? These are all innovations over the prokaryote. And then we get to the rest of the chapter for the most part. And this is it. I know you guys were like, okay, I'm not breathing anymore here. Right, so yeah, chemistry is hard to do up, right? So basically now when you take a look at this particular scenario, the question that most students have is, do I need to know all of that? And the answer is yes. Because this is your animal cell. This is your plant cell. How do I know that this is a plant cell, not an animal cell? Cell wall, right? That's what stands out, right? What else is different? Let me just kind of go back here. There's your animal cell. Anything else that stands out? Chloroplast. Thank you, Megan. Yep. So that's this chloroplast. What else? There's one more. It's really big. Yep, exactly. This big old vacuole, central vacuole. Animals don't have that, plants do. So basically, I kind of like to mention this one because when we take a look at this, a lot of times, especially at this particular point in the chapter, a lot of times, if you haven't already, a lot of times students will be like, okay, wait a minute, how do I study for this? Because there's just like so much coming at you, right? So one of my big things that I always tell you guys is to figure out a system to index your knowledge. And one of the suggestions that I make, not because everybody's different, right? So you kind of have to find the process that works for you. But one that works for a lot of us is something visual, right? Because it's our dominant sense. Oftentimes we recall images and pictures in our head before words. And this is an example of one of those visuals. So a lot of times I'll tell students, like, every chapter has a set of images, there's usually a fairly small set that kind of encaptures a big swath of the chapter, right? So there's a lot of it in there. And this is one of those images. And so if your brain already naturally recalls images well during an exam scenario, then you'd be doing yourself a service to sort of burn some of these all-encompassing images into your brain. Because when your brain sits down to an exam, and it sees, and you can recall this picture, then it'll be able to grab onto the picture very easily, right? And it's like, oh yeah, I can see that picture of the cell. Now, here's the thing. Typically speaking, the way you trick your brain, it's like indexing your knowledge, is that oftentimes the stuff, the writing that comes along with it, if you basically memorize the picture along with the writing, when your brain pulls the picture out of that kind of cluttered haystack of thoughts in your head to try to pull this stuff out, it oftentimes will pull everything that you associate with that image out along with it, including all this writing. So oftentimes what I tell students is use this image sort of like a table of contents, like a knowledge index for, and it covers most of the rest of the chapter. There's a couple of other topics at the end of the chapter we'll cover that aren't on here, but most of the chapter is going to be a tour through all the organelles. And so use this as an organizer in your brain to basically allow you to be able to visually pull this out in your head. And not only that, but as you're studying through it, as we go through each of the organelles and sort of add detail and things of that nature, is don't just sort of try to memorize that detail in isolation, because that's what makes it taxing on your brain. You'll remember this one, but you won't remember the detail in a few slides, right? So what you want to do is you want to try to transfer that detail to this slide. Tell your brain, listen, it's okay to only remember everything that's on this slide, right? And the idea is, as you study through it, let's say you study through and you kind of like go through all this and you're like, okay, I got all this stuff. But then the next time you sort of study through it, add another line of detail as we cover it in lecture, and then study that along with everything else. And then when you go through it again, add another line. And then as you study it again, add another line. So what you're doing is you're burning this image into your brain, but you're connecting as many lines of detail to this image so that when you remember that in an exam, it pulls out as much information along with it as possible. The more of those lines of detail you can sort of pull out with this image, the more likely you're going to be able to answer more questions correctly. And that's a really good strategy, because every single chapter, generally, especially in today's market, because everything's so visual, has a group of these types of images where they just sort of pull large chunks of the chapter together, right? So that, like, if I were to say, listen, I have a limited amount of time. I got to work, I got to run, I got one thing to study. I can study one thing. That's it. What is it? It's one of these, right? So rather than going over page by page by page of notes, if you can transfer it all into one nice tidy place like this, then it allows your brain to sort of pull it out, and sort of, you're kind of like sticking it to this image, and that's allowing your brain to sort of pull it out. A lot of you will be like, well, I can easily turn this to flashcards. You can, but I would not suggest doing that alone. And here's the reason why. Because flashcards, basically what they do is they eliminate context. And oftentimes understanding what's going on in biology requires you to understand its context. So yeah, you could flashcard out cytoskeleton. That'll only get you through the definitional problems, right? It won't get you through the context problems, because context requires something like this. And this is the reason why I'm a big fan of this, is because this shows you the context. It doesn't just talk about cytoskeleton. It talks about cytoskeleton within its proper role and place in the cell, right? So it's got a place to be and a job to do. Flashcards can't capture that. I'm not saying don't do flashcards. I'm saying don't do them exclusively. Because part of the problem is when you do flashcards, it's just kind of like a big pile of clutter in your brain. So when you sit down to the exam, you're like, I don't know any of these answers. Yeah, that's right. That's because your brain is trying to pile through just this relentless pile of random flashcards. And you didn't give it any kind of organization. You didn't give it any context. You didn't give it anything your brain needs to make sense out of all these little random bits of information. So it's like basically trying to find Waldo, and you're like red, green deficient. So everything's gray. Okay, so no, I'm not stopping. I know you guys are all about, I can hear the cheering at home. That's of all the two people that are actually still at their computers. I know how it works. It's gonna log in, and Gonna do some binge watching on Netflix on my phone. You guys are like, crap. How do you know that? Is he watching me? It's like, no, because I'm the. What do you think I do during meetings? It's like I say, you know, we're all the same. We're more alike than different. Okay. This is going to go fast, and it's intended to go fast because I'm giving you yet another system for indexing knowledge, right? So the visual index is a good strategy because your brain is very visual. This is another alternative strategy, something you can do with every single chapter, regardless of what kind of images are in there. This is just basically an outline. Every single chapter can be outlined pretty clearly. There's usually about 2 or 3 major pillars in every single chapter that can be subdivided out. And that is a great way to help also index your knowledge as well. So this is basically organelles by functional grouping. Not functional groups, functional grouping. There's 4 major functional clusters of organelles. The first one is going to be the informational organelles. And that's going to start off with the nucleus. Okay, and that's going to be where we start off with. This basically houses the DNA. Within the nucleus is going to be a nucleolus. This is basically an aggregation of ribosomal RNA, not membrane bound. There's no membrane here. It's just a pileup of ribosomal RNA. And then also in this group is ribosomes. We already talked about ribosomes a little bit, but this is basically a protein complex that makes protein. It's another one of those evolutionary circular reasoning things, right? It's one of their chicken egg moments in evolution that makes things challenging and interesting. So those are your main informational organelles. They have to deal with information storage, information use, information processing, okay? Then we're gonna get to the next one, which is the endomembrane system. Now, the endomembrane system has a series of organelles in it, and there's a particular process that ties a lot of them together. And I'm going to add a couple things in there to kind of ties a whole bunch of them together. We're going to start off the endomembrane system with, first of all, your endoplasmic reticulum. And there's 2 different versions of the endoplasmic reticulum. There's rough, ER, which basically is involved in protein synthesis. And there's smooth ER, which is involved in calcium storage. We'll talk more about this later when we get to that. It's also involved in lipid synthesis and in detoxification. Then from the ER, we'll move to the next step to what's called a transport vesicle. I'm going to put that one here. This is basically a membrane bubble that houses crude protein that has been made in the ER, right? So we'll talk a little bit about that once we kind of get to that point. And then from this transport vessel, because it's transporting this crude protein, then it moves on to the next major organelle, which is the Golgi apparatus. And the Golgi apparatus's job is to modify, sort, and ship the protein to the next step, which is the secretory vesicle, which is basically a membrane bubble. That houses the finished protein. Now, this whole process, this right here, describes a pathway for something we'll be talking about called the secretory pathway. Now, in addition to this, I like to add 2 more organelles. Oftentimes, they're added to other places, but because they're an offshoot of this process, I like to add them here. That is basically the lysosome, which is the garbage disposal of the cell, or the recycling center, depends on how you want to look at it. And then the last one is the peroxisome. Which basically looks at oxygen detoxification. We'll talk more about that one. Now, the third major functional group is the energy relateds. And there's 2 major one of these. There's the mitochondria. And its job is to make ATP. And then you have the chloroplast, which does photosynthesis. Now, those 2 are the subject of our energetics chapters, right? So chapter 7 is all the activities associated with mitochondria, cell respiration. So that's what chapter 7 is about. And then chloroplast, the activities of chloroplast, photosynthesis is what chapter 8 is. Okay, so these have entire chapters unto themselves. And so we don't spend a whole lot of time on these guys because they got entire chapters to unpack what they do. And then the last one is your cytoskeleton, which is basically the skeleton of the cell. And you have 3 major fibers. So you have microfilaments. This is in order. Intermediate filaments. And microtubules. All of these guys basically can be summed up functionally as support and locomotion. So let's begin with the first. The nucleus, right? So the nucleus basically is your dumping ground. It's the repository. It's basically where you have deposited all of your genetic information, your DNA. Right? So the DNA is your master blueprint. So it is true that most eukaryotic cells have a single nucleus, like most cells in our body have a single nucleus. However, there are some that have more than one nucleus, like our skeletal muscles, for instance, can have more than one. But that's rare. And there's usually a very, very, very specific reason why you would have more than one, if you do have more than one. The nucleolus, remember, this is a non-membrane structure. Is an aggregation of ribosomal RNA. And what's ribosomal RNA? This is a structural component of ribosomes. So basically, you're kind of making the structure of the factory, right? So typically a cell nucleus that has a lot of nucleoli in it, and generally speaking, you'll see kind of like a nucleus, and you'll see kind of like these little aggregation, there's like little dark spots inside the nucleus. Those are nucleoli. Those are that little pileup of ribosomal RNA. That's usually a pretty good sign that this is a nucleus who's busy about the process of making protein because it's busy making those manufacturing centers, right? Those ribosomal kind of manufacturers. And so the nuclear area is surrounded by not one, but two phospholipid bilayers. So it's got actually two layers of lipid membrane. And then of course, because you need to get access to your blueprint, right? You're going to have traffic into and out of the nucleus. But think about it. Your master blueprint is highly secured, yes? Does anybody need access to that master blueprint? Think of it this way. Think of the president. The president is a fairly secured person, yes? You can't just walk up to the guy and shake his hand. You'll probably get shot or whatever, thrown on the ground at least by Secret Service, right? Well, the Oval Office, which is inside the White House, right, is the president's office. That's where he works. And the individuals who have access to the Oval Office is a very short list, right? So obviously the president is there, but typically the individuals who get access to the Oval Office only get access. Why? Because the president needs them there, right? So you're talking to only the president's closest advisors, maybe his chief of staff. And, you know, he's got maybe a half dozen, usually an average president, maybe I have a half dozen of their closest advisors, and they have access to the Oval Office. Why? Because it's like they're part of the president's daily debriefing, right? They basically come in there, they got to debrief them on what's going on in the world, what sorts of decisions are pressing, what they think is happening, right? If there's action that needs to be considered, and then you get all that sort of stuff. But guess what? You're only in that office if you're summoned. So even if you're the chief of staff, you don't just get to walk right on into the Oval Office and say, you know, hey, Joe, how's it going? Right? No, right? It's a highly secure area. Why is it secured? Why can't Joe Average, like me, just walk right on into the White House and just cruise right on into the Oval Office? Yeah, why would I need security clearance? What's the purpose? What's the purpose for having security? What are you trying to do? Protect what? Yeah, not the information. It's just an empty room, right? But you're trying to protect the president himself, right? And that's the reason why you don't have access to the Oval Office. By the way, that's not just that, but even like, you know, Schumer, who's kind of like the big dog in the Senate, he can't just walk into the Oval Office. The Speaker of the House, like Pelosi, for instance, I'm not sure that the current Speaker of the House would be welcome in the Oval Office, but you know, somebody like Pelosi, she couldn't just blow right on into the Oval Office, right? Even if you're really, really high level and you got lots of clearance, like even the Department of Defense. I mean, one would argue probably one of the individuals who probably have one of the highest levels of security clearance is probably the Secretary of Defense, right? Because they're the ones who basically have to sort of manage all the military secrets and all that sort of stuff, right? So they're like pretty high. Even that person can't just blow right on into the Oval Office. So your presence in the Oval Office is by invitation only, right? Not only that, but the passageway into the Oval Office is highly guarded. Same thing is also true for the nucleus. You have highly securable and highly vulnerable information, just like the president, right? You cannot allow your DNA to get screwed up. Why? Because if I screw up your blueprint, are you going to turn out like you? No, you're going to, I don't know what you're going to turn out into, right? But it's going to be something considerably more of a train wreck if I go in there and start scrambling up your blueprint, right? So you have to secure it. So only individuals, only molecules that have a reason to be in the nucleus can be allowed to pass in. But that basically means you need to get things in and out of the nucleus, which basically means you need nuclear pores. It allows you to have passage, regulated passage, not just passage, into and out of the nucleus. Now, when you take a look at the DNA that's in there, oftentimes students will have this sort of misperception that the DNA that they have in there is just kind of like all this floating twisted rope ladder that's in there, right? That's kind of what's floating around, and that's actually not the case. The way DNA exists inside the nucleus is in a form that's called chromatin, which is actually a combination of proteins and DNA. So you have DNA plus protein, both of them. So what are the proteins? So inside your chromatin, you have actually this drum-like complex of proteins made of what's called histones. So this is like your histone drum. And you have several of them. These are like little complexes. There's like 8 different histones that make this little protein drum. And then your DNA is actually wound around these little histone drums. So this is what chromatin looks like. So that DNA, that protein then protects the DNA, right? Because if you were to touch DNA, pull on it, it'd be like pulling on a cobweb, right? What happens when you pull on a cobweb? It just disintegrates, right? That's exactly what happened to the DNA molecule if you just grabbed on it. So the protein allows it to have structure and protection, okay? And that's kind of what you find inside your nucleus. So let's take a look and see what's inside the nucleus. So here's your typical nucleus. You can see you got your nuclear pores are on the outside, basically just a bunch of proteins that are inserted into the membrane. Remember, you have you have 2 membranes. Remember, you have an inner and an outer membrane. And it basically punctures right through. So here you can see down here your pore complex. So you can see here's your inner membrane, here's your space, and here's your outer membrane. And you got these proteins that are basically inserted into this ring-like structure, creating this sort of circular pore. But it's not just an opening, right? Because you have to regulate it. So what you have on either surface is on the inside, you got what's called this nuclear basket structure, which has these little cytoskeletal fibers attached to a protein, which is attached to more cytoskeletal fibers, which kind of holds everything together, right? But this kind of allows for regulation of the traffic. So you can think of it as sort of like there's a sense of sort of like a doorway guard, right? So there's somebody guarding the doorway to the Oval Office so that you can't just blow right on in there. And then on the cytoplasmic side of it, you'll see more little cytoskeletal fibers that kind of connect to the outside of the cell itself. So that way you can kind of have your nucleus anchored to the rest of the cell. So it's all kind of in position, okay? It's not just random. But this allows for regulated traffic. And then you can see this double membrane system. And then on the inside, you'll see you've got in your nucleoplasm, you'll see this is all your chromatin here, all that little dark and light purple, that's all your chromatin. So that's where your DNA just kind of all laid out there. And then this little structure right here, which is unfortunate, but because of the 3D graphics of computers, they don't have a way to do this. But that's the nucleolus. It's not an actual ball, right? The problem with it being a sphere for 3D graphics is it makes it look like there's sort of a hard, rigid boundary in the structure, but there's not. It's largely just kind of like a general sort of a gamish. As a matter of fact, oftentimes if they would have done better if they had just cut this out because that is not as well defined a boundary. It's just a pile of ribosomal RNA. A little bit of a misleading image. Oftentimes, the most common mistake on an exam like this is students will call that the nucleus, and that would not be right. That's the nucleolus. So that's where all that ribosomal RNA is. And then in this pore complex, you'll notice another thing that's just right underneath the inner membrane, and that's this little orange layer right there. That's called the nuclear lamina. So on the inside of the inner membrane is this kind of like little structure called the nuclear lamina. And that's what we see here. So this is our nuclear lamina, which is like a gauze-like set of fibrous proteins that are on the inside of this. This is basically an intermediate filament of what we just talked about. This is part of the cytoskeleton. This is a type of intermediate filament where you have long fibers of protein made of laminin. That's those fibers. So it makes long fibers. And so these long filaments of laminin will form these long fibers that then crisscross like gauze. And that's what's on the inside of the inner membrane of the nuclear envelope. So what does this do? The nuclear lamina basically gives the nucleus its shape. If you didn't have that, then the nucleus would basically collapse like a deflated balloon. So the laminin, that nuclear lamina, is a structural framework that kind of keeps the tent up, right? So if you didn't have the shell, the framework of the tent would just basically collapse down on you. That's what happened to the nucleus. And it would collapse down on all the DNA, and it wouldn't be all that structural and that functional. So that's a perfect example of the role of an intermediate filament, cytoskeleton speaking. Now, these two images here, this is a scanning electron micrograph of the outside of the nucleus. So you can see all these pores. We're not just talking about an occasional pore. We're talking about lots of pores, lots of nuclear pores. So lots of traffic going in and out. And this is a transmission electron micrograph where you can see here is the outer membrane, the inner membrane, and this is the nucleus in here. And this is your cytoplasm out here. So you can see the double membrane system. There's your outer, there's your inner, and then you can see they come together here in a little opening, and that's your pore. That's a really, really great set of images, scanning and transmission. So you can see how those two different types of electron micrographs gives us a lot of structural information, especially in how an actual nucleus looks like. So let's take a look at the ribosomes, right? So the ribosomes are something that occurs in all three domains. That basically means all cells have it. And so what you're doing then basically is you take a protein, it's a protein complex where you have ribosomal RNA and protein in this complex. And what it's going to do is it's going to take a special type of RNA, right, which is the copy of your protein, and it's going to turn that along with the help of transfer RNA. We'll talk more about this in the last chapter that we cover in this semester, the process of protein synthesis. And it turns that into protein. And so the ribosomes in eukaryotes are kind of useful, right? Because we can basically have these little protein factories. We can either have them free in the cytoplasm, just scattered all over the place, or we can have them associated and tethered with membranes, right? Which is particularly helpful because if this particular manufacturing site, this particular factory is going to be associated or specialized in just making, say, for instance, nuclear proteins, then I can have a mechanism to tether that ribosome to the nucleus. That way, when it makes its protein, it releases the protein already there at the job site, ready to roll, right? If I have a protein, for instance, going to be made, it's going to be active in the cytoplasm, then I can have the ribosome free in the cytoplasm. So when it makes that protein, the protein just folds up and it's ready to go. It's already on the job site. You don't have to transport it across long distances. Makes it much more efficient. Why basically transport stuff if you can just locate the factory there, make the product, roll it out, and sell it locally, right? That basically saves a lot of costs on distribution. And that's kind of what you can do with ribosomes because you can basically move them around. You can place them wherever you want. And so we see lots of different types of ribosomes. So here's what they look like. So you can see that basically a ribosome has two primary subunits, has a small subunit and a large subunit. We'll see the activities of this and all the active sites and the functionality of ribosomes in that last chapter, because this really is that protein synthesis story. Okay, we'll start off next time with the endomembrane system.